Okay, so I guess let's start. So we're super excited to have Nick talking to us about this very recent new work about the discrete Gaussian, and as I understand it, about sort of the distribution of convolutions of discrete Gaussians, which is something that comes up sort of all over the place in lattice crypto and also in lattice algorithms. So Nick is currently a postdoc at Rutgers with Stephen Miller. Before that, he got his PhD with Daniele, and he's just generally kind of cool. So we're excited to have him. And right, so if you have questions, please type in chat either the question itself or just the fact that you have a question. Try not to interrupt the speaker sort of mid-sentence, because with the lag, that tends not to work so well. And with that, I'll let Nick start.
Thank you. Yeah, so I'll be talking about our work, Improve Discrete Gaussian and Subgaussian Analysis for Lattice Cryptography. This is joint work with Daniele Machancho, Chris Piker, and Michael Walter, and this is to appear in PKC 2020. Okay, let's see. There we go. So the goal of our work, it's to provide a simple framework for analyzing discrete Gaussians. So like a simpler and modular approach for analyzing them. And if you look in the literature, you'll often see that many of the discrete Gaussian like convolution theorems or the discrete Gaussian analysis theorems, they're all kind of proved from scratch each time, but at least in spirit, they're all extremely similar. Like they all boil down to like one or two smoothness conditions. So our hope is, or was, maybe we can have a simple theorem or a simple smoothness condition such that it would imply all of these other analyses. And hopefully this would give like a modular framework for future analyses of operations on discrete Gaussians. And what we found is, yes, there is a simple characterization, and it's usually after maybe one or two steps, you can always show that the analysis boils down to the discrete Gaussian being smooth in the kernel of some linear transformation. Okay, so an overview of the talk. First, I'm going to give some background. Then I'm going to talk about linear transformations of discrete Gaussians. And then next, I'm going to talk about a tighter analysis of generating Elderberry samples with discrete Gaussian error. And then after that, general convolutions of discrete Gaussians. And as a secondary contribution of our paper, we have some tighter analysis on Subgaussian matrices. Okay, so this is the lattice seminar. We all know what a lattice is, but just to review, a lattice is a discrete subgroup of Euclidean space. Equivalently, you could take all integer combinations of some basis. And importantly for us is the dual lattice. So this is it's also a lattice, and it's the all the vectors in the span of the lattice, the linear span, that is, that when you take the inner product with the lattice and these vectors, you get you land back in the integers. Okay, so most of the talk we're going to be talking about discrete Gaussians. Just to review, the discrete Gaussian over a lattice lambda, it is the probability distribution such that the probability of sampling a vector x in the lattice is proportional to the Gaussian function. And important for us is the Gaussian width. This tells you how wide the distribution is. And you can also have a non-zero center. The center doesn't need to necessarily be in the lattice. Later on throughout the talk, often we're just going to work with s here equals 1. And so if you see this row without a subscript 1, that just means s is equal to 1. And also, we're going to throw away the center, because you can always take the discrete Gaussian over the lattice coset. So shift all the points by the center, and then have a zero-centered discrete Gaussian, but it's on a lattice coset now instead of a lattice. Still, everything's perfectly defined. Okay.
Sorry, Nicholas is Hotek. Can you hear me?
Yes, I can hear you.
So you can do this shift, but that means that you have to make sure that all your theorem statements don't just apply to zero-centered lattice, but to shifted lattices. Is that correct?
Right, and they do.
Okay, so should I just be so henceforth I should just think about shifted lattices?
Yeah, so this equation is what, so if you do want to shift the lattice to a non-zero center, that you can always have this equation in your mind, right? So you can always take it over a lattice coset and then shift, just add this vector C.
So I guess all Nick's saying is that like there's sort of two different ways that people tend to describe like a shifted discrete Gaussian. Like one is like as a discrete Gaussian over a lattice that's where the distribution itself is shifted, and the other is like a distribution over a lattice coset, and he's just pointing out that these are the same thing. So I guess, and you're saying that you're going to use like the ladder notation, like the distribution over a coset as opposed to the distribution over the lattice with a shifted.
Correct. Correct. Yeah.
Cool.
And this is what we do in applications too. We usually shift or usually sample on a coset and then shift by a center anyway. Okay. So in applications, often we'll have a non-spherical discrete Gaussian. This is where, say, you take a positive definite matrix sigma, and then now the probability that a x here is sampled is now proportional to the row function with this inverse covariance matrix here. And we write square root sigma because there's many different square roots that you can take for each sigma. And sometimes picking them wisely might help you with analysis, with the like analysis and the proof maybe, but in the end, it's still the same distribution. Okay, so as we all know, discrete Gaussians are kind of ubiquitous with lattices and mathematics, cryptography, and complexity. So we have a question.
So the question is how to think about a non-spherical Gaussian geometrically.
Let's see. One simple way is if you have a invertible matrix, you could just map the discrete Gaussian. So that would shift everything, morph the distribution. But really, it's going to be, instead of concentrated around the sphere in Euclidean space, it's going to be concentrated around like an ellipsoid. So like when you think of discrete Gaussians, or Gaussians really, you usually think of like a blurry sphere. And in a non-spherical discrete Gaussian, maybe a blurry ellipsoid. Okay, so in mathematics, discrete Gaussians, they give some of our tightest transference theorems. These are theorems relating the shortness of vectors in a primary lattice compared to the shortness of vectors in the dual lattice. They give us, in lattice cryptography and complexity, they give us our tightest worst case average case reductions. In algorithms, they give us the fastest algorithms to solve SVP and CVP exactly. For lattice signatures, they give us our digital signature schemes that have the smaller signature size. For advanced trapdoors, they're at the heart of many of our applications like IBE, ABE, GGH15 multilinear maps and its applications, and also something such as like function hiding FHE. Okay, so let's see, is my bar blocking? There we go, okay. it's not too hard to plot a one-dimensional discrete Gaussian over the integers. And what you'll notice is if you take the discrete Gaussian and then shift it, so you take a discrete Gaussian over the integers and then shift it by the point farthest away from the integers, or 0.5, you'll see a noticeable difference in the Gaussian mass of these two distributions, or these two functions. Now what you can do is you can actually make the Gaussian much wider. And then when you still estimate the Gaussian mass, it doesn't matter where on the real line you pick, the Gaussian mass is going to be almost the same, or it's not noticeably different. And when thinking about the Gaussian function, there's two equivalent ways to think about this. This is either the same mass here could be gotten by taking the integers and scaling it by 1/10, and then just having s here equals to 1. So really, this is kind of like, this is a statement about the density of z, in a sense. Okay, so now these previous pictures, they motivate smoothness for discrete Gaussians. And intuitively, all we think about when we think about if a discrete Gaussian is smooth is whether or not it behaves like a continuous Gaussian.
Nick, sorry, so take again. Can you go back to the previous picture, the previous slide again?
Yes.
What would you like us to pay attention to in the two pictures? They look identical to me. Is that the point?
Yeah, okay. So this is actually off center. So
I see.
when you're taking Gaussian mass, it doesn't matter if this is 0.5 or 1,000.5. It just matters how far you are away from the lattice. So that's why I picked such a small center.
I see.
And 0.5 is the farthest away you can get from the integers.
And sorry, I'm still not quite sure. What should I be paying attention to in the two pictures? That the two Gaussians, they are not the same, right?
Right, but their mass is almost the same. So like their mass is not noticeably different. Whereas before, in this much more narrow Gaussian, or much like less dense version, the two Gaussian masses are noticeably different.
Okay. So I think when you say mass are the same and not the same, is it sort of the same way we talk about being two distributions being statistically close?
Yes. So that in the end, that's very related. Yes.
Okay. Thanks.
Okay. So we're gonna talk about that. Yeah.
Okay.
Okay. So yeah. So looking forward, we are going to use smoothness to argue that distributions are statistically close. Yeah. Now, before we get there, though, I have to define the smoothing parameter. And so if you fix some small epsilon greater than 0, the smoothing parameter, it's this kind of funny quantity that is asked, how far do you have to push away the points in the dual lattice such that the Gaussian mass is at most 1 plus epsilon. And you'll notice here that you can't get rid of this 1 because you always have 0 in a lattice. But really, this is a statement about the density of the lattice, because if you scale the dual by s, you're scaling the lattice by 1 over s, or 1 over s. Okay. And then just loosely speaking, we'll say like a discrete Gaussian is smooth if its width is greater than the smoothing parameter for some negligible epsilon. Okay, so smoothness continued. We can extend this to non-spherical discrete Gaussians via the same manner. You could take some square root of a positive definite matrix, and then you ask if it is greater than the smoothing parameter if, when you push away the dual lattice points by this matrix, this invertible matrix, if the Gaussian mass is less than 1 plus epsilon, or equivalently, if you can scale the lattice by the inverse. Okay. Now, importantly for us are the consequences of smoothness. So the Gaussian mass, when you're working with a smooth lattice, it's going to be approximately 1 over the determinant. And if you were to have an s here that's different than 1, this would be s to the n over the determinant. And if this were a sigma, you would have like the determinant of sigma. And really importantly for us is that the Gaussian is shift invariant. So this is something that we're going to use repeatedly today, like over and over again, that the Gaussian mass is shift invariant, or the Gaussian itself, the distribution is shift invariant. And this of course happens for discrete or for continuous Gaussians because shifting the center is just a change of variables and the integrals are equal. Okay, and also importantly for us, or for applications, we have efficient algorithms. So that's more or less what give us all of our applications, so we can sample these distributions efficiently. And also, so where smoothness first came about were tight worst case to average case reductions for SIS. So if you have a smooth lattice, then generating an SIS instance is given by taking a Gaussian over Rn and then taking the Gaussian mass modulo the lattice. Okay, so now I'm going to talk about linear transformations of discrete Gaussians. The simplest case we can think of is what happens when we have a injective linear transformation. Then you can see pretty quickly that these two distributions or these two statistical experiments are equal. You can first sample the discrete Gaussian, and then you can map by the linear transformation, or you can just sample from the range immediately, given by what you would get by the transformed distribution, or the transformed, the mapped domain and the mapped covariance or shape. Okay. Now a little bit more advanced is what. Okay. Is T here linear transform? Oh yeah. So for this to make sense, T, yeah. So the lattice coset must be in the same spaces or in the span of T. Yeah, correct. Or it must be in the range. Yeah, T is defined on the span of the lattice. Okay. All right, you're welcome. Yeah. All right. So a little bit more advanced is, say we have a smooth lattice, say just that it's not full rank, and what would be the Gaussian mass if we were to take and affine, or if we were to take and affine some of this lattice, so if we were to kind of push it away from its span? Well, the Gaussian mass, we would think, would decay proportionally with how far away we are from the lattice's original span. And you can see that mathematically by writing out the center, or writing out this C as an orthogonal decomposition where lambda is in the span of lambda and C perp lambda is orthogonal to the span. And the reason is that once you have orthogonality, this constant term pops out of the Gaussian function. But that is, okay, here we go.
Nick, let me just see if I understand. So you're saying that like this fact that you told us before, that if you shift the lattice by some vector and you're above smoothing, the mass doesn't change. This is true if the vector's in the span of the lattice. It's sort of necessarily not true if the vector's not in the span of the lattice, because sort of if you go orthogonal to the lattice, then just sort of all vectors get farther away from the origin. So like mass just has to go down. So now you're like handling the more general case when you're shifting outside of the span of the lattice, and you get this term that like depends on the orthogonal part of C. of the shift.
Yes,
Yeah?
exactly. Yeah. And really we can see it by this picture, right? So if we take the lattice, and this is the span of the lattice, and we shift it, first you could see that, okay, the Gaussian is a radial function, so it should decrease with how far away we are. And we need smoothness because we want this to be independent of whatever coset we're in up here. Okay. So this picture is going to help us later on too. All right. So a slightly more complex case is, what about orthogonal projections? So real quick, say we have a general lattice coset. Say we have P as a subspace, which we call a lattice subspace. And what that means is that the intersection of the lattice and P is full rank in P, or that this intersection lattice is a full rank lattice in the span, or in P. And if we have that the lattice in this direction is smooth, when we project out when we project out this direction, then the following two experiments are statistically close, which we're going to see why in a second. But this is taking a discrete Gaussian over the coset A and then projecting orthogonally to P. Or you can just project the coset orthogonally to P right away and take a discrete Gaussian over that projection. Okay. So why is that? If we look at the right-hand side here, so we want to fix a V in the projection of A, and then really the Gaussian mass is going to be proportional to everything we project out. And you kind of have to tilt your head here because the picture, it's rotated compared to the last picture. But we're going to see that what we really need here is this shift invariance. So it doesn't matter which coset we pick, as long as the Gaussian, or as long as we are smooth in that direction. Okay. Okay. So what about a general linear transformation and a general discrete Gaussian? So just to set the table, T is here, again, a general linear transformation. A is a lattice coset. We have some small number epsilon. S is full column rank. And we have that A is inside the span of S. And we also have that the kernel is a lattice subspace. So the lattice is full rank in the kernel. Now, with these, the most important thing to consider is that the lattice is smooth in the kernel. So it's full rank. This is just so what you get is a lattice. But really what we need is this condition, this smoothness condition. And if you have the smoothness condition, then these two statistical experiments that you could run are statistically close. So you can take a sample from the lattice and transform it, or you can sample directly from the transformed domain and shape. So more concisely, we just need a smooth kernel for this to hold. And right away, it might not seem that obvious, but what we're going to see is that this kernel condition is going to appear over and over again in applications and the theorems we talk about.
Sorry, this whole thing again. Sorry, the kernel condition, the equation that stands out on the left hand side is a smoothing parameter. I thought on the left hand side is a number, and you have less than or equal to S, which is a matrix. Did I misunderstand something?
Okay, so the smoothing parameter is defined for a lattice, correct? And this is a lattice. This is the lattice restricted to the kernel of this transformation.
And eta epsilon is a number, no?
Yes, yeah.
So what does it mean for a number to be less than or equal to a matrix?
Well, that's one way to think about it is the singular values. So if this is equivalent to the singular values being greater than this number, right? But this is the notation that we use repeatedly. That so we say if this was just a number, this would be how far away in the dual do we have to push out the lattice points such that the Gaussian mass is small. The same thing happens here, except now you have an S inverse.
So Nick, are you really thinking about eta epsilon as eta epsilon times the identity matrix, and the less than or equal to means that the difference between two matrices is positive, definite?
That's equivalent to, yeah. So you could if you want to work with squares, so you could take the square and the identity, and then you could work with S times S transpose, that'd be sigma. And then, yeah, then it'd be a statement about the eigenvalues, say.
I don't think it's equivalent. It's like sufficient, but it's not necessary, right? So this is just, it's an abusive notation. It means that if you scale the dual up by S, then the dual has mass less than 1 plus epsilon. Or like equivalently, if like you apply S inverse to your original lattice, then it should be smooth. Right, so it's just abused notation.
Right.
I see.
Okay. And before we continue, it's important to note that a special case of this theorem was proved before our paper was online. This is in the paper that's going to appear in Eurocrypt 2020 by Dukas, Galbraith, and Prest, and you. So some similar analysis later down the line could possibly be done with their theorem too. Okay. All right. So as the first application, let's look at generating Elderberry samples. So quickly to review, the Elderberry distribution is you're given a truly uniformly random vector A with integer entries mod Q, and you're given a inner product with a secret vector S, and you're going to scramble the low order bits. And here we're only going to concern ourselves with E taken discrete as a discrete Gaussian. And most often in applications, we're going to express these in matrix form. So A here is going to be some, so if we have, say, M samples with M, which is larger than N, we can express this as a short and fat matrix A. And then the inner products, there you could just view them as treating A as a generator matrix for a code, say, and then the errors are just this independently sampled low norm vector. And the Elderberry distinguishing problem is when can you distinguish this distribution from getting something that's truly uniformly random? Okay, so from the very beginning, we've had these Elderberry self-reductions where you have Elderberry samples and you want to generate new samples with the same secret, and you want them to be close to statistically independent from each other, or the errors to be independent from each other. But it's important to note that the previous self-reductions, the proofs, if you were to go to analyze, you'd have to artificially add continuous Gaussian noise, and this would make the proof indirect, but it would also add some a slight artificial bump in the noise. Now, it's important to note here that the reductions themselves were discrete, but the proofs were continuous, or added some continuous noise. So a question is, can we do this directly without this artificially added continuous Gaussian noise? Okay. And then whatever we do, So here in this picture, this $ just means like some independent randomness. We take some Elderberry samples, and we want some Elderberry samples of independent noise. And mapping the uniform case to uniform, that's pretty easy. That should happen regardless. Guess that is there why we need n log q samples to uniquely recover S. Let's see. So the reason I have n log q is we're going to need this actually, the step that I said was easy. It's mapping uniform to uniform is easy when you have that many samples. Yeah. And that's often how many samples we have in applications, because we'll switch between using A as a matrix for Elderberry and A is using as, say, a matrix for SIS. And once you have this many samples, you know SIS solutions exist. Okay.
What here is uniform? The error is uniform, or the whole distribution is uniform?
Right, yeah. So what I'm saying is whatever we do, it should just map uniform to uniform, right? Like, and that's kind of like the easy step, or that's always been the easy step.
I see.
Yeah.
Okay.
So we're really focused about generating Elderberry samples, but we don't want to mess up that part too.
And when you say new independent LWE samples, you mean like the matrix A should be independent, or the matrix
Yes.
A and also the error?
Yes, yeah, the error and the matrix A, yeah. Cool. But we can't change the secret, right? The secret is still there, yeah. Okay. Many of you have seen this before, but it's the reduction is more or less the same as previous reductions. You say we have these Elderberry samples. Okay, so now I'm just going to reframe in terms of taking Elderberry samples and generating more Elderberry samples. All right, so we have this, like these Elderberry samples of memory, and then we want to, we want to generate more Elderberry samples. So what do? We first take a m-dimensional discrete Gaussian, map to a new vector A, and then use that same vector, inner product it with what we have here, and then add a little bit of smoothing noise. Okay, and now the mapping uniform to uniform part, this happens as long as we are over the smoothing parameter of this lattice, right? So this Q area lattice, or this SIS lattice. And we have tight bounds on this from previous. So I think the tightest bound is in maybe MP12. Okay, so that the sanity check is good. Now, what about the error here? So first, conditioning on this A times X1 gives us this A. The distribution of the error term is this E transpose X1 plus this X2, all right? Now, if we treat this, if we were to separate this from, say we separate the discrete Gaussians, you could treat this as a linear transformation, a simple linear transformation, taking just the inner product with E transpose with one appended, and this this discrete Gaussian over a coset of this SIS lattice with this the last entry just being in the integers. And what is our shape here? It could be non-spherical if these are ones and if R1 is not equal to R2. So we just write it out as diagonal. But you see right away that we can express the joint distribution without any effort. So now all we have to do is analyze the kernel, right? Okay, and using the linear transformation theorem, the kernel pops out with a little bit of thought, not too bad. So first, the kernel of this linear transformation, it's just all real vectors here. That would be V and inner product, or I'm missing a minus sign here. Should be a minus sign. And if you take it with the intersection of the lattice, you get the same thing, except this V is now in the, this V is now in this perp lattice. Okay. And with a few more lines of effort, which will go through the paper, we show with no artificial increase in noise that this is now a discrete Gaussian sample where you can sum these together. Of course, the noise does grow with this error term, but that's always been there. Okay.
Nick, I guess you do need something slightly stronger, right? You want to say that it's also independent of the original E. So you have to like add like, I don't know, some identity or something on there.
Let's see. So I did a little disservice here. I should have written out what the transformed lattice would be, but with a little bit of thought, what would it be? It would be the transformed discrete Gaussian, right? So it would be a discrete Gaussian over Z, and the noise here would be some combination of the E, the R, and the RIs.
I see. So you recover the E. Okay.
Yeah. So E comes out in terms of the width of the noise, but but you don't. So let's see. Yeah. So this is if you know this is if you know the size of E, right? And in the actual reduction, you have to do a little bit of guessing in terms of E.
Oh, I see. That makes sense.
Yeah. But in terms of generating Elderberry samples, we have this R1 and this R2, and then it just has to be larger than some condition on, some function of the norm of E.
I see. Okay, that makes sense.
Mm-hmm. Okay. And in applications, often we know the bounds on E. Okay, so now let's see what this gets us for general convolutions. Okay, so the simplest discrete Gaussian convolution or discrete Gaussian sum of samples would be, let's just take two full rank discrete Gaussians and add them together, right? And make them spherical, just to start. And this is done in Bonnet and Franklin in 2011 in their paper on linearly homomorphic signature schemes from lattices. So say we take this X1 from over a discrete Gaussian over a coset A1 of width S1. Same thing for X2, but different coset, different width. When would this X1 and X2, if we add them together, when would it be statistically close to a discrete Gaussian? So if you recall the last slide, what we did, the first thing we did is we wrote out the joint distribution. And here the sigma is just the identity matrices blocked together. Okay, and we express this as a linear transformation. The linear transformation is very simple, just this identity matrix concatenated with itself. And if we just blindly were to shove this into the linear transformation theorem, we would need that we would need this discrete Gaussian to be smooth over the kernel, intersect the original lattice, and that is just all set of vectors v and minus v, such that they're in the intersection. Okay, let's do a sanity check. So why would this intersection come up naturally? Well, if you fix a z in the range, which is a1 plus a2, then the Gaussian mass that's mapped onto it is going to be all in this set. So it's going to be all sets. So say you pick some representative from A1 and A2. It's going to be all vectors of this form where you have the A1 and the A2, and you have this K and the intersection such that it cancels. So you see that right away, this kernel appears naturally from the first step of the analysis. Okay. And this is, yeah, our kernel. Okay. So oftentimes we can't just glue them together and get the joint distribution without a little bit of thought. So this next theorem is going to be when can we do that, right? So when can we take an experiment where, say, we sample x1 from this Gaussian over some lattice coset A1, and then if we shift the coset of the second discrete Gaussian, maybe by a transformation, when can we just express this as a single discrete Gaussian? And if you remember, the main tool from the earlier slides is that discrete Gaussians, they're shift invariant. So if we're shifting in the second lattice coset, what we need is that this lattice needs to be smooth. So if we have that this lattice is smooth, then you can express this as a single discrete Gaussian. How can everyone think of a lattice product in the previous lattice? Lattice product in the thing. Oh, okay, yeah, okay. That's a good point. So this cross product is just all the set of vectors concatenated together, where the first n coordinates is just a vector in A1, and the second n coordinates are a vector in A2. And this, so if we just look at the lattices, this contains this sublattice. Yeah. Where'd my bubble go? Here we go. Okay, cool. Okay, so back to the slide. Really, what should be setting off alarm bells here is if we're shifting this second coset, we need this shift invariance that smoothness gives us. So that's why we need this second lattice to be smooth. There's always a little bit of lag. Okay. Oh, no. All right. So if we were to just write out these probabilities, on the right-hand side, you would condition, or just naturally on the left-hand side, say you would first condition on x1. And then, so in this distribution, you would condition on x1. And then how would you express that conditioning event for this distribution, which is a single Gaussian sample? It would be that this simple linear transformation, the identity concatenated with 0, when you map it, you get this x1 back. Okay, so when you do that, so this is how we can see that just in the first step of analyzing this, the kernel pops out naturally. Okay, so now we're going to see like a modular approach to proving Chris's convolution theorem from 2012, or from 2010. And say we do the same thing, but now we have a spherical Gaussian, or two spherical Gaussians. And this happens a lot in applications because we're doing some operations, say in signatures, and if you were to just return the signature without without any convolution, you would be leaking information about the secret keys. So instead, what you do is you would take some perturbation that where you would pick this sigma 1 wisely, such that when you add these together, you can cancel out these like cross variances for these dependencies. So the statistical experiment is you're taking x1, this is like the perturbation that doesn't depend on the key, and then you're taking it and randomly shifting this second discrete Gaussian by the first. And then you want to return this x2, which would be, say, a signature. Okay. Now, if we could blindly treat these like continuous Gaussians, right away, we would have that you would get be in the correct range because we did a little shift. And then also that the covariances would just sum, so you could cancel out any dependencies on secret key material. Okay, but it's not that simple. But really, it's not too bad once we start thinking about what we've done before. So the first thing we need to do is express this as a single discrete Gaussian. And from before, as soon as we start shifting the second lattice, this coset, there should be alarm bells going off in your head saying, oh, we need smoothness here. We need this to be shift invariant. So if we have this shift invariance, then we can treat this as a single discrete Gaussian with the appropriate shape or covariances. So there's going to be some dependence on x1 here, or some cross variance, and then some sum here. And then what we do is we just take the simplest linear transformation, which is this 0 and 1, times this distribution now, which would be the second vector. And then we have to make sure that we're smooth enough in the kernel. So here, the kernel, it's actually lambda 1 plus the 0 vector, but I just wrote lambda 1. And if we're smooth enough there, then we are, then the output is actually this distribution. So this is now inside for the discrete Gaussian. So it would be statistically close to this, which is the distribution that we want. And when you first look at this theorem, you see this kind of strange sigma 3 shape, or this sigma 3 matrix. But this arises naturally because you can simply like block diagonalize the sigma, and then sigma 3 then pops out. Okay, so the general recipe for this modular approach, it's first express your statistical experiment as a single discrete Gaussian, then express the output of the experiment as a linear transformation of that discrete Gaussian, and lastly, show smoothness in the kernel lattice. Okay, so where does this idea show up? It shows up kind of everywhere in wherever this analysis arises. So in Regev's Elderberry paper, Chris's 2010 paper, Bonet Franklin 2011, MP12, which is on trapdoors or strong lattice trapdoors, MP13, which is about Elderberry and SIS with small parameters, function hiding FHE, discrete Gaussian sampling, and our signature paper last year. Okay, so any questions before we move on to the last part of the talk? Okay, great. So a secondary contribution of our paper is just some tighter analysis on Subgaussian matrices, or Subgaussian random matrices. So a random variable x is Subgaussian with parameter s if its tails are dominated by a Gaussian of width s. As you would expect, the discrete Gaussian is Subgaussian, and say bounded random variables are discrete Gaussian. Okay, a random vector in Rn is Subgaussian if it's Subgaussian in every direction, or if you take if the inner product of this random variable over R is Subgaussian for any unit vector u. Okay, now in applications, we're really worried about the singular values of Subgaussian random matrices. So that is just a random matrix where its rows are taken as independent Subgaussian vectors. And the singular values are the square roots of the eigenvalues of this cram matrix. Okay, so we're going to just denote S1 of R here as the largest singular value. Yeah. And now this is a random variable. Okay, so why are we motivated to look at this? So if you remember the SIS problem, so say we have this A here, which is the same matrix as before. It's short and fat and uniformly random modulo Q. And the SIS problem is if you're given this random matrix and you're given this random vector mod Q, you have to find a short vector X that maps to this when you take the matrix vector multiplication. Okay. And now really this is a problem over the lattice coset. So I'm missing a parentheses A here, but this is a coset of the Q-Avery lattice defined by A. Okay, so our motivation is, say in a trapdoor scheme, what we have is you have, say, a public verification key as this random matrix A, and then your secret signing key is this random matrix R with small entries, such that when you map this, when you take the product, you get this gadget where this G is any matrix where SIS is easy. Okay. Now in applications, what this allows you to do, it allows you to sample a discrete Gaussian, oh, I'm missing an A here again, over the Q-Area lattice of width that depends directly on the largest singular value of this trapdoor matrix. So really, the underlying hardness of our SIS problem scales directly with the largest singular value. So we want to have say a tight understanding of this parameter. Okay.
So sorry. So here you're saying that things are kind of layered on top of each other, right? Like so, like for MP12, like actually the statement that you just said, the fact that this trapdoor sampling algorithm does this is itself a consequence of your convolution theorem, right? Like.
Yeah, so we don't prove a new convolution theorem. We kind of just
right.
show that the modular way gives a simple proof.
Right.
But yes, yeah, so exactly, yeah. But now we're looking at different random variables in a sense. Yeah. Okay.
Cool.
Okay, cool. Now, so the previously known singular value bounds for, say, a random matrix with independent Subgaussian entries with parameter S, there's this unknown constant that floats around, and they're very tight. Or, so another bound that's commonly used is if you have independent Subgaussian rows, then you get this quadratic dependence on the Subgaussian parameter S. On the smaller dimension. But right away, you'll notice something is wrong, because if you scale the matrix, this should scale also. So this is only for isotropic rows. These are rows that, yeah, the expectation of the cross variance is just the identity. So really, you would expect everything here to scale linearly. So the first thing we do in our paper in this last section is we actually go through the proofs and we find what this constant is. It's about 38. Oh, we also show that it does scale with the standard deviation, as you would expect. But this constant 38, it's kind of, it's almost too large to be of consequence in applications. So then we looked at experimentally, what is this for commonly used distributions and independent entries. And then there we find something much more interesting in my opinion is that the singular values, they're tightly concentrated around this quantity, which is sigma times the square root of the dimension m plus the dimension n. And we have something similar for the lower bound on the least smallest singular value also. And this is interesting because this is exactly what you get for a Gaussian matrix. So for Gaussian matrices, this is known as Gordon's law. So for commonly used distributions, these singular values, they're basically behaving like Gaussians. It's kind of some law of large number phenomenon is going on. And you can see that it adheres pretty tightly to this heuristic. So this is the heuristic, and this is, say, are you using the discrete Gaussian to provide? Okay, so that's a good question. So the question was, are we using the discrete Gaussian here? And that was one of the experiments. We also did continuous Gaussians as just like a way as a sanity check, and then uniform over plus or minus 1, and then another distribution. So yes, this does hold for discrete Gaussian entries.
Okay. So morally, what this is telling us is that like if you're sub-Gaussian, that's no worse than being Gaussian.
Yes. Yeah.
But so is there an example of an uncommon distribution for which this result doesn't hold, for which like you can be sub-Gaussian and have independent entries and still somehow have larger singular values than?
I haven't found it, but I'm sure there is, because it seems like this sub-Gaussian machinery is just too big of a hammer for like the commonly used distributions in cryptography. But I would expect that you could find one. Yeah.
I see.
Yeah, because importantly here we're using independent entries, right? And this is for this weaker bound is for independent rows.
Oh, so you're saying with independent entries, probably this is just true for all sub-Gaussians, but with independent rows, that's much more subtle.
Potentially. I don't know if I'd go that.
Okay, yeah, I'm putting conjecture in your mouth, sorry.
Yeah. So sub-Gaussians, it's also a very broad umbrella of distributions, right? So it's, we didn't explore too far under this umbrella. We kind of just stayed home and isolated. Okay, and then yeah, so these are some experiments as the dimension increases, and it holds for the matrices. Or here this is just for uniform over plus or minus 1, but we saw similar behavior for every distribution we talked about before. Thank you. Any questions?
Okay, so I'll clap. You can unmute yourselves and clap if you're into that. Okay, so now questions. Okay, so maybe I'll go first. So you had Chris's convolution theorem, right? So Chris's convolution theorem, I hope I remember correctly, it says that like you should sample like a continuous Gaussian, and then you should sample from a discrete Gaussian shifted by the continuous Gaussian that you sampled, right? And you're saying that like the framework that you provided in the first half of the talk like doesn't exactly account for this, because like it doesn't exactly account for when the shift depends on like one of the Gaussians or like the first Gaussian or whatever. But then you like jumped really quickly to sort of not care about that anymore. You switched to a different distribution where you're just sort of adding up two Gaussians, right?
So let me
okay, yeah, maybe you can
see if I got this clear. So you're saying here that you could take this to be continuous, right?
Oh, okay. Yeah, so I know it as being continuous, but fine, you take it to be discrete. That doesn't bother me.
So Right, but in Chris's paper in 2010, the general statement is for discrete Gaussians. So we don't beat that by any means. And if you take this A1 here, this lambda 1, if you make it denser and denser, the continuous statement does pop out, or should pop out.
Sure. Okay, but I'm asking something much dumber, which is like, what step did you, like, what was the step that you took to fix this x1 being in the wrong place?
Okay. What do you mean by the wrong place here?
Like, so you have that the shift of 8 that you take for the second discrete Gaussian depends on x1.
Mm-hmm.
But your theorem, I think, doesn't work for that, right? Your theorem, you should take 2 Gaussians that are sort of predetermined and like add them up or something, right?
Oh, okay, yeah. So that's why we talked about joint distribution. So I did make a jump. So that's this statement here. So you express it as one discrete Gaussian.
I see. And so this is like another application of smoothness.
Yes, exactly.
Sort of pre-processing.
Right. And smoothness here, all we need is that the second part is smooth because we're randomly shifting, right? And smoothness is helps us in terms of shift and variance.
So you're saying like this is like a more immediate application of smoothness. Cool.
Yes. Yeah.
Very cool.
So, all right. Thank you all for coming.
Okay. Who did that? That's cool. Okay. So thanks everyone. Maybe we'll stick around for a little longer in case people have questions. But I guess I'll stop the recording now. And thanks, Nick.
Yeah, thank you for having me.